Alright, hello everyone. Welcome back to the Calculus Fun Room. In this video, what I want to discuss with you is derivatives of trig functions. So in the prior couple videos for 3.1 and 3.2, what we discussed were things like the power rule and the product rule and the quotient rule. And ultimately those conversations, or the purposes of those conversations, were to create shortcuts. We didn't want to use the limit definition. So remember, for any function f of x, we had defined the slope of the tangent line as the limit as h goes to 0 of what we would call the quotient, the difference quotient. So I don't really want to go through that process every single time I take a derivative. Right? We want shortcut rules, and that's the point of this chapter. So we're looking at the trig functions. So what I want to do first, I don't want to go through this definition here to develop the derivative of the trig functions. Let's look back at kind of the process we did in, I think it was the video for 2.7. So what we did in 2.7 is we didn't focus on formulas, we focused on concepts of slopes of tangents. So what I want to do is let's consider the function y equals sine of x. Here's the function y equals sine x. And what we want to do is, below that, let's construct the graph of its derivative. So what we did back in that video is we would focus on particular points of interest first. So for example, we would look at points where the tangent was horizontal. Right? So the slope is 0 there. So the slope of the tangent is the value of the derivative. So at this particular x value, the slope is 0. So we would come down here at this x value and plot a y value of 0. And then again, we would move over here. At this x value, we can see the tangent is horizontal. So the slope of that line is 0. And we would come down on the graph of the derivative and we would plot a y value of 0. And we would continue, right? Here's another slope of 0. We would have an x-intercept there. And then another slope of 0. So we would have an x-intercept there. All right, now what we were doing back in that section, right, again, this construction of the derivative, when we would move off of those points of interest, so for example, as I move along the graph in this direction, we would envision the slope of every possible tangent line. So for example, if I move slightly to the right here, and I look at that tangent, is that a slope that's positive? And then I look at that tangent, it has a slope that's steeper, it's a bigger positive. I look at that tangent, is a slope that's bigger. And then now as I move continuous in this direction, the slope becomes a little flatter, right, a little smaller than this one. The slopes get a little smaller, slopes get a little smaller, and then the slopes come back to 0. So these are all positive slopes. They start off small and get bigger. So I have a positive y value that starts off small and gets bigger. Now we can see at the origin, this is the steepest tangent line. So it's the largest y value on my graph. And then the tangents start to get flatter and flatter. The tangents start to get smaller and smaller. The slopes of the tangents get smaller and smaller. And we see a shape something like this. So this was the process back in 2.7. We would construct the graph of the derivative. Now if we do this a little bit more, right, here's a slope of 0. So there's our slope of 0. When we move just off that slope, that point, the slope is negative. And compared to the next one, right, they're getting bigger and bigger, right? So this line is kind of flat, this line's a little steeper, this line's a little steeper. And when I get to this point, this is the steepest tangent. So I have a negative small, right? So the line, the slope is negative, and I get values that get bigger and bigger. The tangents were getting steeper and steeper. And then this point was kind of the maximal value. So we see the maximal value there. And then as I continue to move, this is a little flatter, this is a little flatter, and we come back to 0. So the slopes get smaller and smaller and come back to 0. So roughly something like that. Now, sine is a periodic function, so we should see the derivative continue in that periodic manner. Now, if we look at this graph, we can intuitively see that this is the cosine function. So it looks like the derivative of sine is cosine, right? Cosine passes through 1 at the origin, and then it has pi over 2 as its first x-intercept, right? And this is pi over 2, the maximum for the sine function. So just through a construction, kind of exploratory process, we can see that it seems reasonable that the derivative of sine is cosine. Now, if we were going to do this in more of a formal development, we would technically need to use the definition of the derivative. So if I think of f of x being sine x, which is what we just started with, right, we're looking at applying this definition. So I'm going to have the limit as h goes to 0 of sine of x plus h minus sine of x all over h. Now, in the prior video for 3.1, we talked about the derivative of the exponential, and we took the same approach. We plugged into the definition of the exponential, and what we ended up with was a limit that we couldn't really evaluate by hand. We had to numerically explore what that limit would be. And we actually have the same sort of situation here. We don't know how to evaluate this limit by hand. Now, we could do a little bit of simplification. And what would that look like? So this expression in the numerator, sine of x plus h, we could use an identity, right? So from a trig class, we have an identity of like sine of a plus b. So sine of a plus b is going to be, this expression is going to be sine of x times cosine of h plus cosine of x times sine of h. So using an identity, we can split up sine of, let's say, a plus b, or sine a cosine b plus cosine a sine b. And we have the limit as h goes to 0. So in our simplification here, what I'm going to do is I'm going to bring this sine over to this term, and I'm going to group those together. So I'm going to have sine x cosine of h minus sine x, and then I'll just put this last. Say cosine x sine of h all over h, take the limit as h goes to 0. And then I'm going to do a little bit more simplification. So first of all, I'm going to take this fraction and I'm going to break it up. Right? So I'm going to think of this as, let's say, a over h and b over h. So I can split my fraction up. Sine of x cosine of h minus sine of x. I'm going to put all of that over h, and then I'll subtract as a separate fraction cosine x sine h all over h. Technically, I'm doing the limit as h goes to 0 of that whole expression. And again, this is a legal split up, if you will. Sorry, that is a plus sign. This is a legal split up, right? Because this is two fractions with a common denominator. And if I add two fractions with a common denominator, I write one big fraction, and then I add the numerator. So I have this term plus this term, and that's what I have here. So we're just going backwards from a common denominator and just splitting this up. Now doing a little bit more algebra simplification, if you will. In this first fraction, I'm going to factor the sine x out. And then I'm going to have times, let's say, cosine h minus 1 all over h. So I'm factoring the sine x out of that. And then I'm going to take the cosine x out of this, if you will. And I'm going to have sine h over h. Okay. So just doing some algebra simplification, right? Obviously, if I multiply this back into the numerator, I end up with this numerator. And if I take cosine x and multiply to the numerator, I end up with that. So I haven't done any legal work algebraically. I'm just simplifying expressions. Now, when we look at the limit, right, of like f times g plus the limit of, let's say f times g here, right? So properties of limits say that I can take the limit of a sum, and that's the sum of the limits. So I'm going to take the limit of the sum and write it as the sum of the limits. So just using properties of limits to write this expression here. And these limits are h going to 0. And then I also have a property of limits that says the limit of a product is the product of the limits. So the limit of this product here is going to be the product of the limits. So I'm just going to make that simplification here as well. So just doing some algebra cleanup and then some cleanup in regards to limits. And again, I have cosine x times sine h over h. So the limit of a product is the product of the limits. I forgot the limit symbol there. So I have the product of the limits. Right. And at this point, we have one other simplification we can do. So in regards to the limit here, the limit is involving the variable h. H is going to 0. Now granted, x is a variable here. However, in the limit process, the x is a constant, really. So the limit of this constant is the constant. So as h varies to 0, sine x goes to sine x. And then I'm looking at this expression with all of the h's in it. Okay. And then ditto over here, cosine of x is really constant in regards to the limit process. This has no h's on it. So that's really cosine of x, and then times, we have the limit of sine of h over h. All right, now we get to a point where we have to evaluate these two limits, and we don't have the tools by which we can do that in an algebraic manner. So we could look at a geometric derivation of these limits, and in fact, any calculus book will do a thorough, rigorous mathematical proof of those expressions. But we're just going to do an exploration, save a little bit of time here, do an exploration, and let's see what those limits look like. All right, so I paused the video real quick just so I could bring up some graphing technology, a calculator to evaluate this limit for me. So again, what we're looking at this first time here, so we're looking at cosine of h minus 1 all over h, and h goes to 0. Now I'm using Desmos. Desmos wants variables here of like x. So I'm writing this as cosine x minus 1 over x as x goes to 0 just for the purposes of Desmos. Keep in mind these are really h's as our limit. So I have the expression cosine h minus 1 all over h, and here's my values of h as h goes to 0. And we can see what happens as h goes to 0. This expression here is going to 0. We have negative 0.0499. We have negative 0.004999. This is negative 0.00005, right? There's 4 decimal places, scientific notation. Now 5 decimal places, negative 0.000005. So these values are going to 0. So we can see what's happening in this expression here is this, all of this is going to 0. So in other words, we have 0 times sine x, and that's a big old 0. Now I want to explore this expression. So let me pause the video, type that in my graphing calculator. So looking at sine h over h as h goes to 0, we're looking at sine of h over h, and we're looking as the h goes to 0, we can see that expression approaches 1. So we can see this expression here is approaching 1. So we have minus, and I think that's a typo that I have there, is it not? I think that's a plus sign. It is a plus sign, right? This is a plus sign here. This should be a plus sign here. Apologize. So we get 0 plus, this is a plus sign, and then this is 1 times cosine x. So we have, using the definition of the derivative, we have shown that the derivative of sine x equals cosine x. So from the graph, we deduced that the derivative of sine looked like cosine, and then now using the definition, we have shown that the derivative of sine is cosine. Now, we could go through the same type of process for all 6 trig functions. We could look at the derivative of cosine, we could look at the derivative of tangent, we could look at the derivative of secant, cosecant, cotangent, so on and so forth. So again, just to save a little bit of time in this video, let's not go through all of those derivations, but let's summarize what those derivations would provide. So it doesn't matter the order in which we do these, right? But let's say we looked at the derivative of cosine of x. We would get that derivative is negative sine of x. If we looked at the derivative of tangent, we would see that derivative is secant squared. If we looked at the derivative of, I guess let's do cotangent next, we would see that's negative cosecant squared. If we did the derivative of, what am I missing? Derivative of secant of x, I'm running out of digital paper here, that would be secant of x times tangent of x. And then if we looked at derivative of cosecant, we would see that's negative cosecant cotangent. So these would be the 6 formulas, if you will, our shortcut formulas. So just like we had the derivative of a polynomial term, right, a power rule, doesn't really have to be a polynomial, x to a power, we had the power rule. We talked about the derivative of the base e exponential being derivative of e to the x was e to the x, and then now we add to that knowledge the formulas for derivative of trig functions. All right, so at this point in a textbook, usually the conversation focuses around, now that we have developed the derivatives of the trig functions, let's just put them into practice. So let's, build the skill of differentiating functions that involve the trigonometric functions. Now keep in mind the bigger picture of derivatives here, derivatives give us a measure of a rate of change, right? If the function represents a position or height, the derivative is instantaneous velocity, right? So we have rates of change having different applications. We will come back and revisit those applications, but for the moment, let's focus on the skills of using those formulas. So kind of at a first example, right? Let's say example 1, we want to find the derivative with respect to t of t squared times sine of t. Now what I'm going to start to do is use different variables here, just to get us comfortable with the idea of our derivative operator. That's supposed to say number 1. So whether the independent variable is x, this would say d over dx of x squared sine x. That would indicate that x squared sine x, x is my independent variable. I'm taking the derivative of the independent variable. The letter doesn't really matter here. So in this expression, my independent variable is t. So I'm differentiating with respect to t. So again, this is the differential operator. It says take the derivative of this expression with respect to its independent variable. So I'm differentiating this function, and I notice that this is a product, right? So I should be thinking of the product rule. Now remember, the product rule said that if I was differentiating the product of 2 functions, that could be written as derivative of the first times the second plus first times derivative of the second. So that's the rule I'm using here for this product. So I'm going to differentiate the first times the second. So here's my first, here's my second. So the derivative of the first times the second plus, and then the first, which is t squared, and then the derivative of the second. So the derivative of sine is cosine of t. I like to put parentheses around the inside of the trig function. So I'm going to try to stick with that. So product rule, t squared times sine t. Derivative of the first is 2t times the second, which is sine, plus the first, which is t squared, times derivative of the second, which is cosine, that we just wrote on the prior slide. Okay, so let's do another example. And in this example, I want to do a quotient rule. So let's suppose we have f of x equals sine of x over cosine of x. I like parentheses around there, and we want to find f prime. Now, some of you are probably saying, now wait a second, sine x over cosine is tangent, and we already wrote the formula for that, and that is true. But let's do this problem like we didn't know that, and let's do the quotient rule. And then what we should end up with is the derivative of tangent. So we wrote on the prior slide, the derivative of tangent is secant squared. So let's do the derivative of this as a quotient rule, and we should get secant squared. All right, now let's remind ourselves of the quotient rule real quick. So if I have a quotient of two functions, f over g, and I'm taking this derivative, I do bottom times derivative of the top minus top times derivative of the bottom over the bottom squared. So that's what I'm going to do in this case, right? My top being sine x, my bottom being cosine x. So again, this says bottom times derivative of the top. So I have bottom. And then derivative of the top, derivative of sine, is cosine. And then minus, now I have top times derivative of the bottom. So top is sine x. And then derivative of cosine is negative sine. And then all over the bottom squared. Okay, so there's the quotient rule. We're finished, technically, with the quotient rule, but I want to do some cleanup because that surely does not look like secant squared that we're supposed to have on the prior slide. So let's do a little bit more cleanup. So cosine times cosine is cosine squared. Cosine squared. And then in this case we have minus times minus, which is a positive, and we have sine squared. Now, you may remember that what we have in the numerator here is the Pythagorean identity for trig functions, which is cosine squared plus sine squared equals 1. So I'm going to replace the numerator with 1 because cosine squared plus sine squared equals 1. So I get 1 over cosine squared. So here's f prime that we have. And then remember that 1 over cosine is secant. So 1 over cosine is secant. I'm just reminding myself. I don't know why I wrote that there. So let's remind ourselves that 1 over cosine is secant. So what we have in this case is secant squared. Okay. So if my function is tangent, right? What we just proved is that if my function is tangent, then its derivative is secant squared. So we just proved that formula that we wrote on the prior slide. I wanted to practice a quotient rule, so that was the approach that we took here. But obviously in a homework problem that you would be working on, if you have tangent, you're not going to want to work through a quotient rule here. You're just going to want to say tangent has a derivative that's secant squared. All right, so I want you to do one for me here. All right, so I'm going to give you the function y equals, let's say, e to the x times tangent of x. What I want you to do for me is find y prime. So I want you to pause the video. I want you to attempt this one on your own, and when you're done, unpause and come back and we'll do this one together to check your work. Okay, so now that you have attempted this problem, let's see what you got. Now, keep in mind, in this case, we're looking at a product rule. This is really similar to the very first example that we did. So if I do my product rule, right, I have the first times the second. So I'm going to do derivative of the first, and I'm going to write this out with prime notation. Right? So here's derivative of the first times the second plus first times derivative of the second. So let's write out what each of those terms would be. So what's the derivative of e to the x? It is itself, e to the x. And then what's the derivative of tangent of x? That is secant squared of x. We're really done with the derivative at this point. if this was me given a test, I would be happy with this answer. Some solutions manuals are going to factor out an e to the x, which again isn't really necessary. Now there are reasons, there are times when we're going to want to factor, but right now that's not necessary. Right? So we'll see a little bit later when we will want to factor and when that would be advantageous for us. All right, I want you to try one more for me. So I want you to consider, let's say the function is, and you know what, wait a second. I said I was going to change variables occasionally to just kind of keep us focusing on process here. So let's suppose we want to look at sine of theta over theta plus 2 times secant of theta. And what I want you to do is take the derivative with respect to theta of that expression. So again, I'm going to pause the video. I want you to try this on your own, and when you're done, unpause, and we'll do this together. Okay, how did you do? Well, let's go over this together, right? So the derivative of a sum is the sum of the derivatives, so I'm going to write a couple extra steps here. And the derivative of a sum is the sum of the individual derivatives. So I'm going to take the derivative of all the terms here. Okay. And in this case, I have a quotient that I'm going to have to deal with. Right? Excuse me. So when I do this quotient rule, right? So I'm going to have a bottom times derivative of the top. So I'm going to have bottom. And then, again, I'm going to start to get lazy and switch to the prime notation. So here's bottom times derivative of the top minus top times derivative of the bottom all over the bottom squared, and then plus. So now when I differentiate this expression, keep in mind the way that we deal with a coefficient is we in essence pull it out and then we deal with the function. We take its derivative. So we pull the constant out and then multiply it back on at the end. Okay, so what does each of these things do is we simplify. So the derivative of sine theta is cosine of theta. My thetas are getting sloppy. And then minus, then we have sine of theta. And then so what's the derivative of theta? So this is usually a little tricky for most students initially in a Calculus 1 course. Think about when I'm differentiating x, If I look at y equals x, what's y prime, right? And the slope of any line is the slope, right? The derivative of any line is the slope of every tangent. So for a linear function, the derivative is just the coefficient, right? I mean, we could generalize that. We did in the video for 3.1. So if I'm looking at a linear function, y prime is just its derivative. So when I look at this expression, just like the derivative of 1 times x is 1, the derivative of 1 times theta is just going to be 1. All right, and then now the derivative of secant theta is secant theta times tangent of theta. And this is my derivative, and there's really not any simplification I could do here. I mean, there's not a theta that's common for me to factor out. Cosine and sine aren't common. I can't factor that out. So this would really be my final answer. The only other thing I could maybe do is get a common denominator for these two things, right? That's totally overkill, not really necessary. At this point, we're just focusing on finding the derivatives, and here we are with the derivative. All right, in this next example, I want to take a look at the idea of a differential equation. Differential equations is an extremely important subject in many of the engineering courses that most of you will probably be taking. It's my favorite class to teach, honestly. Don't tell Calc 1 class that it's not my favorite. It is. I really love Calc 1, but differential equations, such a cool subject. I did quite a bit of research in my master's thesis utilizing differential equations to model the propagation of coherent light, so like a laser beam. That is far beyond the scope of this class. And in a differential equations course, one of the things you'll do is you'll solve a differential equation. So kind of like you might solve an algebraic equation, x squared minus 3x plus 4 equals 0, where you use techniques of algebra to find the solutions of x for that equation. What you would do in a differential equations course is you would look at, say, that given differential equation, and you're asking what function y will satisfy that equation. Y, its derivative y prime, and its second derivative y double prime. Now in the scope of this class, that's beyond what we're learning. So what we're going to do in this example is just going to verify that y equals 3 sine x is a solution to the differential equation that we have given here. So in order to verify that this is a solution, right, what we're going to do is take our equation y that we are given to verify, which is 3 sine of x, and then we're going to find y prime. So that would be 3, and then derivative of sine x is cosine of x. And then y double prime would be 3 times, and the derivative of cosine is negative sine of x, which of course I could write that as negative 3 times sine x, right? So what I'm going to do then is take y double prime and plug it into my differential equation, right? Take y prime, plug it in, take y, plug it in, and we're going to verify that this function, y equals 3 sine x, is a solution to that equation. So y double prime is negative 3 sine of x plus 1/3. Y prime is 3 cosine of x, and then minus y, which was 3 sine of x. And remember, what we're really doing, we're kind of asking, is this a solution of the equation? And it is going to be, because the instruction said show that it is, right? So let's combine all of the things on the left-hand side. So I would have negative 3 sine x minus 3 sine x gives me negative 6 sine x's. And then I would have 1/3 times 3, which is 1 times cosine of x. And we can see at this point, after plugging in y, y prime, y double prime, simplifying, we're verifying that that function was a solution to that differential equation. So let's take a look at another example, and this would be something similar that you might see in your homework. Now this problem kind of spins the question in a little different way. We're being told that y equals a sine x plus b cosine x will satisfy this differential equation for specific values of a and b being constants. Right, so this might be y equals 3 sine x plus 5 cosine of x, and we're looking for those values of a and b that will satisfy that equation. So very similar to what we just did, we're going to go ahead and find y prime, and we're going to find y double prime. We're going to plug it into our differential equation and find the values of a and b that make that equation true. So let's see, if I'm finding y prime, I have a, and the derivative of sine is cosine. I'm going to have b, the derivative of cosine is negative sine. Let me go ahead and erase my y double prime there, and we'll simplify. So I have a cosine of x, and that's just going to be minus b sine of x. And then we would have y double prime, which would be a, derivative of cosine is negative sine, my negative sine, and then minus b, and the derivative of sine is cosine. So I have minus a sine x minus b cosine x. So my goal here is I want to plug all of this into my differential equation. So I'm coming over here to my differential equation. I'm going to plug all of that in, y, y prime, and y double prime, and then I'm going to simplify, right? Now I'm probably going to run out of digital paper here, so bear with me as I try to organize. So again, let's plug in y prime, y double prime, and y into my equation. So y double prime, we have negative a sine of x minus b cosine of x plus y prime. So I have plus, and my y prime was a cosine of x minus b sine of x. And then I have minus 2 times y, and my y was a sine x plus b cosine of x. And all of that is supposed to equal sine of x. So what I'm going to do, on the left-hand side of that differential equation, let's go ahead and gather the like terms that we have there. So what I'm going to do first is group them all together. So let's group all of the sine terms together. So here's a sine term, here's a sine term, and when I distribute the negative 2, there's a sine term. So I have a negative a sine x, I have a minus b sine x, and I'm going to have a minus 2a sine of x. Then let's gather all the cosines. So here's a cosine, and again, when I distribute the -2, there's a cosine. So I'm going to have negative b cosine of x plus a cosine of x, and then minus 2b cosine of x. And when I add all of that together, it's supposed to equal the sine term that we have on the right-hand side of our equation. So now what I'm going to do at this point is continue gathering the like terms. Now keep in mind, all of my sine terms, right, I'm gonna add the coefficients together. So if I had 5 sine x minus 3 sine x plus 12 sine x, I would add all those together. I don't know what a and b are. So what I'm going to do then is take all of those sine terms and add them. And in essence, I'm going to factor the sine term out, is how I'm going to think of that. So I'm going to have negative a minus b minus 2a. And those are all the numbers in front of the sine function that I'm going to, add together. And then I have all of the cosine terms I'm going to add together. So negative b plus a minus 2b, and those are all of my cosine terms. Okay? So I've added all of the like terms together. So again, my question here really is, right, what are the values of a and b that make this true? So in other words, the coefficients have to be the same. Think about this for a second. If I had ax squared plus bx equaling, 3x squared minus 4x, the only way that that equation could be true is if the coefficients are the same, right? So if a was 3 and b was -4, then those two sides of that equation are equivalent, right? That equation balances. So I'm going to take that same approach, right? So I'm going to have the coefficient of the sine on the left-hand side, and the coefficient of the sine on the right-hand side is 1 times sine. And then I need the coefficient of the cosine on the left-hand side and the coefficient of the cosine on the right-hand side. And since there is not a cosine term, its coefficient is 0. So I'm going to set these coefficients equal to each other here. So the sine coefficient, so let's see, minus a minus 2a is minus 3a minus b, and that has to equal the coefficient of sine on the right-hand side. And then I have minus b minus 2b, and then the plus a. So a minus 3b, and that has to equal the cosine's coefficient on the right-hand side. So in my goal of seeking the values of a and b that satisfy this differential equation, we have now gotten ourselves here to a system of equations. So we have 2 unknowns and 2 equations, and we're solving for a and b as the unknown constants. They're going to satisfy this differential equation. And a couple different ways to do this, right? I could use what we call the elimination or addition method. I could use the substitution method, right? Personally, I prefer to use the addition method. So I'm going to take this bottom equation and multiply by 3 so that minus 3a and plus 3a will add to be 0. Okay. Now don't forget that 3 is going to distribute to here. So I'm going to have minus b minus 9b is going to be minus 10b. And then of course, 3 times 0 is 0. So I'm going to end up with 1 plus 0, which is 1. And I get b is negative 1/10 in that case. Now, if I come back to my second equation, let's find a. So we had a minus 3b equals 0 in that equation. And then we know my b value, so I'm going to solve and add 3b to the other side, and we just found our b value. So a is positive 3/10. So there's the values of a and b that satisfy that differential equation. So we had given the solution, we had been proposed the solution of the form a sine x plus b cosine x, and we now know the values of a and b, and I'll just go ahead and make that a subtraction. Minus 1/10 cosine x. So that is the specific equation that would satisfy that differential equation we wrote in the beginning, which is y prime plus y double prime plus y prime minus 2y equals sine of x. I believe that was what the differential equation was. There it was right there. All right, so two examples there. They just kind of illustrate the arithmetic, if you will. I don't want to call it arithmetic. It's the calculus of solving a differential equation. And in this case, we're only really verifying the solution of a differential equation because we don't really know what techniques we can use to solve of a differential equation. Now, in a Calc 2 course, we will introduce ourselves, one section, we'll introduce ourselves to solving a differential equation. That's a really fun section. But you won't really dive deep into solving the equations until you get to an actual differential equations course. Alright, the last part of the video, I want to take a look at a couple applications here. So in this first application, we have a ladder 10 feet long, rest against a vertical wall. Let theta be the angle between the top of the ladder and the wall, and let x be the distance from the bottom of the ladder to the wall. The bottom of the ladder slides away from the wall. How fast does x change with respect to theta when theta is pi over 3? So let's just kind of visualize the situation here a little bit. So we have a wall. Let's say here's a wall and some ground next to the wall. And we're told we have a ladder leaning against the wall. So let's say here's our ladder. We're told that theta is the angle between the top of the ladder and the wall. So here's theta. And we're told x is the distance from the bottom of the wall, from the bottom of the ladder to the wall. So there's x. So we're being asked, what is, let's see, if the bottom of the ladder slides away from the wall, how fast does x change? How fast does x change with respect to theta? So what we're looking for is the rate of change of x with respect to theta when theta is pi over 3. So what we need to do then is come up with an equation, right, assuming our wall is at a perpendicular angle to the ground. We want to come up with an equation that involves theta and the side x. We have, right angle geometry here. We could look at sine theta, cosine theta, tangent theta, the sides of ratios of sides with the trig function. Now, first of all, I don't know if I should use, let's say, tangent of theta would be opposite over adjacent. But I don't know how high up the wall the ladder goes. I was told the ladder is 10 feet long. So I know that the hypotenuse of this triangle is 10. So that motivates me then to use the ratio of sine, because sine of theta being opposite over hypotenuse. So I know sine of theta will be opposite over hypotenuse. Now, since I'm finding dx d theta, right, we're assuming x is a function of theta, and we're going to take its derivative. So let me go ahead and solve for theta here. I have x is 10 sine theta. And I'm a little crazy, and I like to have my, my dependent variable on the left-hand side. So here I have x as a function of theta, so we can go ahead then and differentiate and find dx d theta. So I pull the 10 out, and the derivative of sine theta is cosine of theta. So here's my equation, my derivative. The derivative gives me the rate of change. We're looking at the rate of change of x and with respect to theta. So in order for me to find the rate of change of x with respect to theta, I need to know the angle theta in my equation, and I'm told that we are looking for dx d theta when theta is pi over 3. So I have 10 times cosine of pi over 3. It's going to give me the rate of change of x with respect to the change of theta. So I can pull out a unit circle. I never memorized the unit circle. I always think of the two reference triangles, 30, 60, 90, which is the one I need, right? And then I could have a 45, 45, 90. So I need the cosine of pi over 3. Pi over 3 is 60 degrees. So cosine of 60 is adjacent over hypotenuse. So there's 10 times a half, and that gives me 5. Now, what are the units of my rate of change? So the dx over the d theta. So the dx is the unit of length, so that is in feet. And then the d theta, so my radian measure for my angle theta. So x is changing 5 feet per radian, right? So as this ladder slides, for every 1 radian change in angle measure, my ladder slides 5 feet per radian. Okay, in this problem I want to take a look at an application of a sort, which involves a trig function. So let's suppose that we have, let's say here's a ceiling of some sort, right? And we have a spring that hangs from the ceiling. Now normally if I hang a spring, right, it just hangs, and then I'm going to put a mass on this spring, and when I put a mass on the spring, it's going to pull it down. Let's say here's the mass. Well, my spring got really ugly. So I'm hanging a weight that is a mass, and it stretches my spring for me. Now at this point, this is what we call equilibrium. So when I let the mass hang and I let it stop, vibrating, this is equilibrium. We would consider this the position, let's say y equals 0, if you will, right? Now I could pull the mass down and let go, and it's going to oscillate. It's going to vibrate up and down, up and down. Or, I could take the mass and I could push it up, and when I let go, it's going to drop and vibrate up and down, up and down. Now, without getting too deep into the math derivation here, let's just suppose that we somehow know, right? Somebody told us that the height, the position of this mass is given by, let's say, 8 times sine of t. Now, if we were to graph this trig function, we would see something along these lines, right? Excuse me. If I were to graph this trig function, 8 sine t looks something like this, right? So the amplitude is 8 down to minus 8. And if we think of the independent variable here, right, is t. So we're interpreting that as time, and we'll write that in a second, right? And then let's say the height, the y value is in inches. So we're going to say the height of this object from equilibrium. Sometimes we call that displacement. So the mass is displaced from equilibrium in inches, and it oscillates as a function of time. Let's say that that's seconds for this conversation. So we can see as time progresses, the height oscillates up to 8 inches, down to 8 inches, up to 8 inches, down to 8 inches, so on and so forth. So this seems reasonable, and that mass oscillates up and down. Now, this model that we have provided here is assumed a couple things for simplicity of our conversation. Is it assumed basically that there's no gravity, there's no friction. Now, in a real-world scenario on planet Earth or some other situation where we have some form of gravity, we're going to have gravity slowing down this oscillation, and eventually it's just going to stop oscillating. It's going to come back to equilibrium. Also, springs provide a form of friction, if you will. So as the mass pulls down, the spring's trying to pull it back to equilibrium. So it's causing a friction. It's an opposing force. When the mass is oscillating above, the spring's trying to push it. Right? As the spring compresses, it wants to push it back to equilibrium. So we have ignored in this model those two forces within the system. There's no gravity, there's no friction. And so what we would see is the motion, right, or the mass oscillate up and down forever and ever and ever. So kind of like we're in space, right? We have no friction or no dampening, if you will. We have nothing dampening the motion here, and it's just going to oscillate forever and ever and ever. So for this example, what I want to talk about is, let's say part A of this problem, what we want to do is, let's say, find the velocity at t seconds. So I'm going to do part A, and I'm going to say find the velocity at t seconds. Right? So what we've talked about in prior videos, back in chapter 2 in particular, right, is that instantaneous velocity comes from the derivative of position. So my velocity as a function of time is going to be, the derivative of my position function. So we're differentiating, what did we have? 8 times sine of t. That's what we were differentiating. So again, I'm going to pull the constant out. I'm going to differentiate the function sine. And the derivative of sine is cosine. I have 8 times cosine of t. So there's my velocity for any time t. All right, and then what are the units of this measurement, right? If I'm looking at the position, the height is inches, and I'm looking at the x value, if you will, the independent variable seconds, right? Then we have, inches per second. That's how our velocity is measured here. All right, so let's say we have a part B, and part B says to find the position, the velocity, and the acceleration. Let's say at t equals 3 pi over 2 seconds. All right, this seems like a kind of funny time to choose, right? I mean, normally we would think of time as whole seconds, right? So at 1 second, at 2 seconds, at 3 seconds. Of course, we could have decimal seconds. We could have t equals 1.5 seconds, t equals 2.8 seconds, t equals 10.79438 seconds, whatever. So we're picking 3 pi over 2 just so the numbers work out pretty with the trig functions. So the position at 3 pi over 2 seconds, right, would be our position function at 3 pi over 2 seconds. So we're going to have 8 times the sine of 3 pi over 2. Now we know that the sine of 3 pi over 2 is -1. So we're going to have 8 times -1, which is -8. So that is the position at 3 pi over 2 seconds. Now the velocity at 3 pi over 2 seconds, right, we just wrote our velocity equation. It was 8 times cosine of the t value. So we'll write that down. Now if we look at cosine of 3 pi over 2, that is 0. So we get 8 times 0, and we have inches per second. Now if we stop for a moment and we think back to our position equation. Actually, let me scroll back up here. So I have 3 pi over 2 seconds, and here is my, my position equation, right? This was 8 times sine of t is what we graphed here. Now the trig function sine, right, has a maximal value at pi over 2. Value is 1. At pi, it has a value of 0. And then at 3 pi over 2, it's down here. Right? So we can see that the position is -8 inches. So in other words, we can interpret that as being 8 inches below equilibrium. So we have a position of -8 inches. That's where we're getting that. We found the velocity to be 0. So we can see the derivative, the slope of the tangent here is horizontal. So our velocity is 0. Now physically, right, what that's saying, so the mass oscillates up, and then for a brief moment it stops, and then it comes down, and then for a brief moment it stops and changes direction, and then it stops for a brief moment, changes direction, comes back down, right? So we're looking up and down as our motion here, right? And so what we've looked at is right at the bottom, so the fullest stretch of the spring, the mass has stopped momentarily, right? So the instantaneous velocity is 0 inches per second. So physically, right, that's what we're seeing within that graph. Now, we also asked for the acceleration. So remember that acceleration is the second derivative of position. So what that means, right, is we're taking the derivative of the derivative, right? So we're really looking at, this is velocity, right? We're really looking at the derivative of velocity, right? So velocity is y prime, right? So y double prime is really the derivative of velocity, and that is acceleration. So we're coming back to the velocity equation, 8 cosine t, and we're differentiating that. So we're differentiating 8 cosine t. Right? This is my velocity. We're taking the derivative of velocity. So I pull the 8 out. The derivative of cosine is negative sine t. So my acceleration function is negative 8 sine t. So I want the acceleration at 3 pi over 2. So I'm going to have negative 8 times sine of 3 pi over 2. Again, we talked about sine of 3 pi over 2 is negative 1. So, I lost my 8 somehow. So I have negative 1 times negative 8, and that's positive 8. And remember, units for acceleration are the units of velocity per unit time. So we have inches per second, right? Or we have inches per second squared. Okay, so I want to do one other problem for you, an extension of this problem, and then I feel like this video is getting long enough, and then we will stop and finish off this section. So let's suppose the next part asks us, what would this be? Letter C, I think? Something like that. I forget where we were. So letter C says, when is the mass at rest? Right? So let's say, when is the mass at rest? So remember, if the mass is at rest, it has no speed. So we're looking for where the velocity is equal to 0 here. Now remember, back in our graph, right, we had 8 sine t, looks something like this, and we said here's where the mass was at rest as it changed direction. Visually, this is where the slope of the tangent is 0. Right? Our velocity is 0. Our derivative is 0. The slope of our tangent is 0. Right? The slope of the tangent line is 0. Right? That's what we're looking for, visually speaking. Now, we already found the velocity of this function. The velocity was 8 cosine of t. So what we're looking for in this case is, where does that equal 0? A couple of different ways to approach this. First of all, let me divide 8 to the other side. 0 divided by 8 is still 0. So we're asking, where does cosine t equal 0? There's a couple different ways that we can answer that question. One way is we could look at the unit circle. Another way is that we could look graphically. I'm a visual learner. I prefer to look graphically, but let's do both, right? So we can connect to both ideas. So what I'm going to do is I'm going to graph cosine function and look where it is equal to 0. So cosine looks roughly something like this, right? Like this, right? And then so if this is x equals 0, this was pi over 2, this was pi, this was 3 pi over 2, and this was 3 pi over 2, and then this was 2 pi, right? It's periodic. So if it's a value of 1 at 0, then it's back to a value of 1 at 2 pi. Have pi in the middle, then we have pi over 2 and 3 pi over 2 as the x-intercepts. Okay, so where does cosine equal 0? Cosine equals 0 here at pi over 2, at 3 pi over 2, going to be 5 pi over 2, 7 pi over 2, 9 pi over 2, so on and so forth. So the solutions to this equation, basically, a couple different ways we could write this. We could say it's pi over 2, and then I add pi to get here. I add pi to get here. I add pi to get here, right? So pi over 2 plus pi is 3 pi over 2. And then I add pi, and I get the next one. So technically pi over 2 plus 1 pi, and then pi over 2 plus 2 pi's, and then pi over 2 plus 3 pi's. So I could have pi over 2 plus some multiple of pi. Pi over 2 plus 1 pi, pi over 2 plus 2 pi, pi over 2 plus 3 pi, so on and so forth. So there's one way for us to write where the velocity would be 0. So where is the slope of the tangent 0? Where is the velocity 0? Where is the mass at rest? These would be the times where the mass is at rest. Okay, so I just paused the video real quick. I did a Google search for unit circle. Now keep in mind what we're solving here. Let me choose the color gray. We are solving where the velocity is 0. That was where the mass was at rest. So remember, on the unit circle, the cosines are the x values and the sines are the y values. So when I look at my unit circle, all of the x values of these points are the values of cosine. Right? All the y values on these ordered pairs are the values of sine. So again, if I look at pi over 4, the cosine of pi over 4 is root 2 over 2. The sine of pi over 4 is also root 2 over 2. So we're looking for where cosine is 0. So we can see here's where cosine is 0. So if we're at pi over 2 units, cosine will be 0. And then down here, again, cosine is 0. We can see if we're at 3 pi over 2 units, cosine of 3 pi over 2 would be 0. And that's exactly what we got from the graph that I drew. And again, we can see here, remember, as we let theta increase, we rotate counterclockwise. So I get pi over 2 as the first time cosine is 0, and then pi later, right, 180 degrees later, pi later is 3 pi over 2, and then another pi, and then another pi, and then another pi, and so on and so forth, right? So if I start at pi over 2, I've added 1 pi, and then I've added another pi, so 2 pi's, then I've added 3 pi's and 4 pi's, and so on and so forth. So from the graph and from the unit circle, we can see that for this example, the mass will be at rest, right, when we have times that are pi over 2 plus k pi. All right, I think that is everything that I wanted to cover in this video. In the next video, we will take a look at what we call the chain rule.